Okay, let us record some more problems. So now we're looking at number 7. It says to take this function and find out everything we can and then graph it. Well, the domain of this thing is from negative infinity to infinity because it's a polynomial. Then we know in terms of intercepts, the x-intercepts are where y equals 0, and the y-intercepts are where x equals 0. So if I set y equal to 0, it means we take x cubed minus 6x squared minus 15x plus 4 and set it equal to 0. This on a high-stakes exam would factor if we use something like our old buddy Desmos or a graphing calculator. We can find that negative 2.10, 0.20, and 7.90 are our x-intercepts. And then our y-intercepts, I think it's pretty clear that when you plug in 0, you get 0 cubed minus 6, 0 squared, minus 15 times 0 plus 4. You just get 4. So that means that 0, 4 is an intercept of that graph, right? Okay. Then if we look for symmetry, again, the idea is you take f of negative x, and if you were to get f of x, then it's an even function, which means symmetric with respect to the y-axis. And if you plug in negative x and get negative what you originally had, your function is odd, and it is symmetric with respect to the origin. With respect to WRT, with respect to the origin. So here we have no symmetry. So here there is none. Because if you take f of negative x, what you're going to get is negative x gets cubed, minus 6, negative x gets squared, minus 15, negative x plus 4. You get negative x cubed, minus 6x squared plus 15x plus 4. And notice that does not equal what we originally had, and it also does not equal negative of what we originally had, so that means we have no symmetry. Okay. Let's see, asymptotes. Because this is a polynomial, there are none. So in terms of symmetry, that's what we had. In terms of asymptotes, we have none because it's a polynomial. So in terms of increasing, decreasing, and decreasing, we know that's going to be a first derivative conversation. So when we take the derivative, I think it's pretty clear that you're going to get 3x squared minus 12x minus 15. And so we know that in general, we said that step 1 was to find our critical values. Remember, that's what we did usually. And then step 2 was to partition. And then step 3 was to chart. So step 1, to find our critical values, which is where the derivative equals 0 or the derivative is undefined. If we now take that derivative and say, where does that derivative equal 0, or where is that derivative undefined? Well, it's a polynomial, it's defined everywhere. But where is it equal to 0? Well, you'd have 0 is equal to our 3x squared minus 12x minus 15. If you pull out a 3, you're going to get x squared minus 4x minus 5. And so you're going to get x minus 5, x plus 1. So we need to be able to factor things like that. But that means that one of those must be 0. So either this equals 0 or this equals 0. Because we know it's ridiculous that 3 can never be 0. So you either get 5 or you get negative 1 for your possible critical values. So then step 2 is to partition. Is that juice good, Eleanor? Partition. So by partition means we cut up our number line into 1, 2, 3 pieces, right? Using either the critical values or where the function itself was undefined, but since it's defined everywhere, we have no extra points. And so now step 3 is to chart. So what do we do? Let's see. If we want to chart, we take our derivative and those pieces of our derivative. So we take 3x minus 5, and we take this x plus 1, and that's going to tell us about our derivative, which tells us about our function. Our intervals, if we read them from the chart, are negative infinity to negative 1, negative 1 to 5, and then 5 to infinity. So then we test a point inside each interval. So for example, at x equals negative 2, it should be clear that we get a negative here, we get a negative here. So negative times negative, our derivative is positive, which means f is increasing on that interval. In this one, how about we test at x equals 0? We get a negative positive, so the derivative is negative, which means f is decreasing in this interval. And then at x is equal to maybe 6, we get a positive positive. Derivative is positive, so f is increasing on this interval, right? So what does that mean? That means f is increasing on negative infinity to negative 1 and 5 to infinity. F is decreasing on negative 1 to 5. And then notice, f prime changes sign from positive to negative at x is equal to what? Negative 1. If it goes from negative to positive, that means f has a relative maximum there. Then we also know that f prime changes sign from negative to positive at x is equal to negative positive at x is equal to 5. So negative to positive means that f has relative min there, right? Okay, so I think that was part F of our graphing, was to find those relative mins and relative maxes. Then if we wanted to look at concavity, we know that is a second derivative conversation, but it's the same sort of deal. Isn't that cool? Yeah. Drink some of that juice, kid. Good job. So second derivative is what? Yes, I'll check that email in a second. Concavity, again, step 1 is going to be to find the critical values. But this time it's going to be setting the first derivative equal to 0 or the first derivative undefined. And then step 2 is going to be to partition and chart. Partition, step 2 is going to be to chart. I'm sorry, not first derivative, second derivative. Second derivative. Because concavity is a second derivative question. Where it is 0 is where we're going to think about where does that concavity change. Yes?
Second means 2.
Very good. Second does mean 2. So, step 1, we're going to find that second derivative. We get 6x minus 2. So if we set it equal to 0, we end up getting, 6x minus 12. 6x minus 12. And so then when we factor out, we're going to get 6 in parentheses x minus 2. And that means that x equals 2 is a critical value of that second derivative. And so what do? Step 2 is to partition. So we take the number line and break it up into 2 pieces. And then step 3 is to chart. So on our chart, we're going to have really just two intervals. We're going to have, let's see, from negative infinity to 2, from 2 to infinity. And then along the top, up here, we're going to have the parts of our second derivative, which is really just 6x minus 2. That's going to tell about that, which is going to tell about this. So I plug in something like negative 100. So at negative 100, I get a negative, which is negative, which means it's concave down. And then at maybe 311, I get a positive, which means the second derivative is positive, which means I'm concave up on that interval. Okay. So then putting it all together, it seems like we would be able to give a rough sketch of what that thing looks like by taking those values that we had, yes. Again, we had those intercepts, those 1, 2, 3 x-intercepts that we had. The only y-intercept that we had was like, what was it, 0, 2, right? 0, 4, sorry. It was 0, 4. So it was something like that, right? And then we know that our max, our local max was going to be over here, we said, if we go back. Our local max was at, what was it? A relative max, excuse me, at negative 1 and a min at 5. So a relative max at negative 1 over here. And then a min at 5, right? So this is not a 0. Burp. At 5, somewhere over here, like 5. And then it goes up like this, yes. Some things to notice here. It is concave down in here. Then it changes to nice concave up over here, right? So that's our inflection point. And that's something that we would know right here. We know that we have, because the second derivative changes from negative to positive at x is equal to 2, that means we have an inflection point. Okay. All right, I'm going to stop here and we'll get some more examples in a second.